see me rolling. They hating, patrolling and trying to catch me riding dirty. 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 We built this city. We built this city on rock and roll. Built this city. We built this city on rock and roll.
To find the average velocity, use the equation velocity equals change in distance over change in time. So if the change in distance was 33.23 meters, divide that by the total time, which was 31.08 seconds, and that equals 1.069 meters per second. So that's the velocity, the average velocity for trial 1, and you repeat for all trials. So by finding the average of each of the 3 trials, you get a total average velocity of 0.971 meters per second.
The equation you use for acceleration is delta x equals initial velocity times time plus 1/2 times acceleration times time squared. So for this car, the initial velocity was 0, so we don't use that. So this car in trial 1 moved 33.23 meters, and the initial velocity is 0. So you do 1/2 times the acceleration, which is what you're looking for, times 31.08 seconds squared. So you end up getting 0.068 meters per second squared as your acceleration. And you're going to continue to do that for trials 2 and 3. So after doing those calculations, you get a total average velocity of 0.057 meters per second squared.
Okay, so to calculate final velocity, do VF equals VI plus AT. And in our case, it started from rest, so VI equals 0, so we don't have to use that. So VF equals AT. And for our first trial, VF equals acceleration was 0.968 times the time was 31.08 seconds, and you get 2.113 meters per second. The average final velocity of the 3 trials is 1.927 meters per second.
For impulse, we use the equation I equals delta P, which is equal to change in momentum. And we know that P equals mv, which is mass times velocity. So delta P equals mass times final velocity minus mass times initial velocity. And since initial velocity is 0, this is 0, so it's just this. And for trial 1, I equals 0.39 times 2.113, which equals 0.824 kilograms times meters per second. And now we'll do the same thing for trial 2 and 3. By using all 3 trials, we find out that the average impulse is 0.753 kilograms times meters per second.
An aspect of our car that was very important was the wheels. We used big wheels in the back and small wheels in the front, and this made it go really far. So having a bigger wheel with a larger circumference was the most effective way to use the wheels.
And we also made a second design, and along with the rest of the class, they both have small wheels in the front and in the back, and we tested both, and we found that this one went less further than that one.
While our design was superior to the others, it's strong!
Strong!
Everyone can improve. So if we had to make one change, we would add another mousetrap that turns the front axle so that we would have an extra source of power and it would go even further and not just be pushed by the back wheels. We assumed friction and air resistance would not be negligible, so we used very thin wheels to reduce friction. And the class used thicker wheels and their cars didn't go as far, so we definitely experienced less friction than they did because of the wheel size. And we made our frame thin and narrow to reduce the effect of air resistance, so it's very thin from the front. We also made this part really long to increase the leverage and increase lever arm, which would be used to transfer energy to the axle, which turns the wheels. One difficulty that we had was being able to attach the string and wind it up. So one solution that we came up with was putting a staple in the tape, which would act as a hook and allow us to easily wind up the string.
Another detail that we have about our car is that we position the trap as far further as possible. Far further as possible. Wait. Another detail about our car is that we positioned the trap as far forward as possible. So the longer the string means that there will be more loops by the string and the car would move at a nice steady pace, whereas compared to the rest of the class, they used a short string which would not allow this nice steady pace. Yeah.
Another improvement that we made to our car was adding tape around the rear axle, which would act as a gear and reduce string slippage. This increased the rate of energy release and allowed the string to be released faster and ultimately increase torque.
Everybody makes mistakes. Everybody has those days. 1, 2, 3, 4. Everybody makes mistakes. Everybody has those days. Everybody knows what I'm talking about. Everybody gets that way. That's right. Everybody makes mistakes. Everybody has those days. Everybody knows what I'm talking about. Everybody gets that way. Sometimes I'm in a jam. I've gotta make a plan. It might be crazy.